Mathematical problem solving is an incredibly important part of not only physics, but science in general, math in general. So I'm going to review that here, but it may be familiar to you from previous classes. So here we have this problem. Roxy is driving a car at this velocity of 31 meters per second. She drives for 400 seconds, and the question is, what will her displacement be? So there are all these different protocols and processes for solving problems and the steps you should follow, but the one that I'll propose here that might be familiar is we're going to identify our givens, what we're trying to find, any equations that will help us find whatever we're looking for with our given information, and then we'll solve the problem at the end. So the stuff that we're given in this problem, we have this velocity of 31 meters per second, so I'll write that here. V equals 31 meters per second. And then she drives for 400 seconds. Now, it doesn't say this explicitly in the problem, but we hopefully know and recognize that as a time that Roxy is driving for. So we're given her velocity and the time that she's driving, and what we're asked for is her displacement. And we haven't covered this yet in class, but displacement is your change in position from the beginning to end of some process or some event. So that's what we're looking for, is her displacement. So we've done our givens, our find, and then I put in parentheses this little s because frequently in physics we don't just use one equation to solve a problem, we might need to use multiple. But in this case there is one equation, and I have a couple up here for us to choose from, although throughout the year our list of available equations will get longer and longer. And these are some not really specifically from physics, although velocity is a little bit, but all of these are sort of chemistry, physics, things that you might recognize. But the equation that's going to be useful for us to find displacement given our velocity and time is going to be this one in the top left that relates those three variables. So I'm just going to write that here. Our v equals d over t, so just shortening that: velocity, displacement, and time. And so now we need to solve this. And an important first step in solving this is just plugging in our given information into this equation that we've identified. So for example, I'm going to put this 31 meters per second in for our velocity. Let me make that a little bit neater. And then we're going to plug our time in where that is in this equation that we identified. So just rewriting this equation, 31 meters per second is equal to whatever the displacement is. So I'm just going to leave that as d for displacement. And then we do know the time, 400 seconds. And at this point, this problem is pretty much a math problem. We've done the physics, we identified the given information, we figured out what we're trying to solve for, we picked our physics equation that will help us get there, and now it's algebra. So we're trying to solve for distance, which means we want to eventually get to a point where we have just d equals something. So the thing that's standing between us and that displacement being isolated is this 400. So right now, d is being divided by 400. So if we want to cancel that out, we've got to do the opposite of that. We have to multiply both sides by this 400 second time. And we can do that because if we're doing the same thing to both sides, the equation still holds true. So that'll cancel out the 400 seconds in the denominator there. And we would just multiply this 400 and the 31 and 400 seconds times 31 meters per second. And that would get us, I think, 12,400. But we always want to make sure that we have units on our answers. And there are a couple ways to think about this. One, the general SI unit for displacement and distance and length is meters. And the better way to do this, and we'll do this more as the year goes on, is you can see that our seconds cancel out, because right now we have 400 seconds times 31 meters per second, so those units cancel out because we have seconds multiplied by 1 over seconds. And so we're just left with meters in the end. So the displacement, how far Roxy will go from beginning to end, or her change in position, would be 12,400 meters as her displacement. So again, given, to find, we picked our equation, and then we solved. I'll see a slightly more difficult example next. So here we have Erica and their notebook, and the information that we have is as follows. So we know that they have a 0.1 kilogram notebook. The density of their notebook is this 800 kilograms per meter cubed, and we're asked what the volume of Erica's notebook is. So the stuff that we're given, 0.1 kilogram notebook. Now again, it doesn't say it explicitly in the problem, but hopefully we know that kilogram is the basic SI unit for mass. So that's the mass of Erica's notebook, is 0.1 kilograms. And then we are given, more explicitly, the density of Erica's notebook, which is this 800 kilogram per meter cubed. I'm going to write that, even though it's D for density, you show that with this little letter that looks like a P. That's a rho from the Greek alphabet, but that's the density of this notebook. So 800 kilograms per meter cubed. And what we're being asked to find is the volume. I'll put that V equals question mark. And it's hard to tell the way I'm writing it right now, but a general tip, usually you write velocity as a lowercase v, and uppercase V would be volume. It's impossible to tell that based on how I wrote this here, but just a general thing. So now we pick the equation that relates these three things, or that would allow us to find what we're looking for, given what we know. So since we know mass and density, if we want to find volume, we can use this equation that relates those three quantities. So we're going to use this one. Our density equal to mass over volume. Okay, so we have our equation. Now we're just going to plug in our given information where we see it being used in the equation. So we're going to plug our density in there. So now it's 800 kilogram per meter cubed is equal to 0.1 kilograms over whatever V the volume is. Okay. So the thing that's a little more difficult about this is we want to eventually get to a point where we just have V, the volume is equal to whatever. But right now our volume is stuck in the denominator here. So we're going to have to actually do a couple steps to not just get the volume out of the denominator, but then to isolate it afterwards. So the first step, since our variable we're trying to solve for is stuck in the denominator, in order to get it out of there, we need to multiply both sides by this volume V. Because what that's going to do for us, it cancels out the volume in our denominator, and it'll get us to this. So 800, I'll keep the units kilogram, meters, oh, let's see, kilograms per meter cubed times V is equal to just 0.1 kilograms. And so now it's easier to see like what we need to do to solve so that we get V is equal to something. Right now we're close. We have V multiplied by 800 kilograms per meter cubed. So if we want to just isolate V, we've got to do the opposite of what's happening to it right now. So we have to divide both sides by this 800 kilograms per meter cubed. And so we can see that will cancel this out, so we'll just end up with V equals. And then on the right side, we've got to actually do this division, so 0.1 divided by 800. So I'll bring up just Google's calculator, and you can always use this if you have your computer but don't have a calculator nearby. If you just search calculator in Google, it will come up with this, and it's very useful. So we have 0.1 divided by 800. And that gets us 0.000125. 0.000125. And then the question at this point would be, what are our units? So we can see our kilograms canceling out because we've got kilograms divided by kilograms. But then we are dividing by 1 over meters cubed, and volume is measured in just meters cubed. Again, the units at this point, we haven't spent much time on this, on like doing that kind of dimensional analysis, so if that seemed weird, I'm skipping some steps. But the important thing is that we know how to arrange our variables and solve for whatever's missing here. So here, Erica's notebook has a volume of 0.000125 meters cubed. Okay, one more example. This one a little tougher, and we're going to be using the ideal gas law here. So hopefully we remember a little bit about this from chemistry, but if not, that's okay. We're really just doing math with it right now. So we have an ideal gas at this pressure of 80,000 pascals, and it takes up 5 meters cubed of volume. And then we're told that the gas is at a temperature of 600 Kelvin, and we're asked how many moles of gas there are in this sample. So let's write out our given stuff. So first, we have this pressure of 80,000 pascals. Okay. We're given also explicitly this volume is 5 meters cubed. We're told that the temperature is 600 Kelvin. Okay, and to find, we're being asked for the number of moles of gas, and in general that's shown as a little lowercase n, is the number of moles, at least in the ideal gas law. Okay, and so the equation that relates these things, the pressure, the volume, the temperature, the number of moles of a gas, is our ideal gas law. And so that's this Pivnert, maybe how you learned it in chemistry. And normally you would just see R in this equation. The only reason that I have this subscript gas here is to differentiate between the two different R's that we sometimes see in physics. So this R here with the gas, that's the gas constant. And then this R here is the resistance of a wire. So just to differentiate, but usually they would both just be R. Okay, now there's one issue that you may be noticing here, and that's that we know the pressure, we know the volume, we know the temperature, but we don't know N. We also don't know what this R is, unless you remember from chemistry. So that R is a gas constant, and if you look over here in the information given to us and the identification of all these variables, it is always that same number, 8.314 joules per mole Kelvin. So I'll just write that down as sort of a given for us. 8.314 joules per mole Kelvin. So we'll be able to plug this number in, even though we're not given it, that's always going to be this 8.314 for the gas constant. Okay, so now we're going to plug the stuff we know into this equation. So we've got our pressure, we've got our volume, we've got our temperature, and we've got our gas constant. And the only thing we're really trying to solve for is this N, the number of moles of gas. So if we rewrite all this stuff, plugging in everything we know, I'm going to leave out units here. That's a bad habit, but since we haven't spent a lot of time on units, and I don't want to get into them here, I'm going to leave them out. So we have 80,000 pascals times 5 meters cubed is equal to whatever N is, that's what we're going to be solving for, times 8.314 joules per mole Kelvin times the 600 Kelvin. Okay. So the first thing to do whenever you have like stuff multiplied together or added or anything like that, if you can, simplify before you have to like do any algebra or like rearranging for your variable. At least that's what I do. You don't have to, and some of you may immediately go to dividing and solving for n, but I find it easier to do some simplification. So I'm going to do this 80,000 times 5, and I think I know what that is, but I know better than to trust myself. So 400,000, cool, that's what's going to go on this side. So that's our simplified 80,000 times 5, 400,000, is equal to n times, and now I'm going to combine our 8.314 joules per mole Kelvin times the 600 Kelvin and see what that is. I definitely don't know what that is off the top of my head. 8.314 times 600. 4,988.4. Okay. So now it becomes a little more obvious what we need to do. So right now we want to isolate n so that it's on its own side. And if we want to do that, right now it's being multiplied by this almost 5,000 number. So if we want to isolate it, we have to do the opposite of that. We've got to divide both sides by that number. So divide both sides by this 4,988.4. And so that will cancel out our number that's being multiplied by n, the number of moles. And then over here, we'll plug this in, 400,000 divided by 4,988.4. And that gets us the number of moles in this sample. Whoa, that's a lot of moles. N equals 80.19 moles. Again, so the only step that was different here between what we did in previous problems and this one, we just had the additional requirement that we had to do some simplification before we started doing any algebra. You could start doing algebra right away, it was just a slightly more complicated equation. But if you follow these steps of going your given, figuring out what you're trying to find, picking the relevant equations to find what you're looking for, given whatever you know, and then solve, that's going to be a very helpful process in physics, in any science class, in any math class, or engineering class you ever take. So it's good to practice, and that's what we're doing here.